In this video, we're going to start discussing the origins of properties of the molecules. So if we think about properties of a molecule, we think about things like boiling point, melting point. We also think about viscosity and surface tension. Like, what does the molecule as a whole, when you have a bulk amount of it, what does it do? How does it behave? Other properties, things like solubility. Does it dissolve in water? Does it dissolve in oil? Does it make its own layer? These are all properties of a molecule. And the origin for a great deal of these is polarity. So today we're going to dive into the origins of polarity. For our molecules, polarity comes from dipoles. We have organic molecules. So these are things with carbons, and those carbons can have bonds to hydrogens, to nitrogens, to oxygens, to halides, and other things. Well, if you have a carbon-carbon bond, they have electrons around them. Those electrons, because you're a covalent bond, they're fairly evenly shared. In fact, for a carbon-carbon bond, if nothing else was there, they're perfectly evenly shared. The idea is both carbons want electrons. They're both pulling on those electrons, trying to draw them towards their positive nuclei, but they're in a tug of war. Both atoms are pulling on them, so that balances out to this distribution. Well, if you think about the periodic table, as you move to the upper right, you're what we call more electronegative. And so the upper right is more electronegative. Maybe remember this in 121, but the idea is the more electronegative you are, the more you want electrons. You pull on them harder. If you're pulling equally, then there's no difference. But if one of your atoms is pulling harder than the other, let's say a carbon to an oxygen, it imbalances those electrons, and they spend more time out in the direction of the more electronegative atom. As a result, you start building up negative charge. Instead of evenly spreading all your negatives over your positives, you start shoving them out onto one atom. That oxygen starts looking a little bit negative, and that carbon starts looking a little bit positive. Well, this is permanent. As long as they are sharing electrons together, this will be a permanent slight imbalance of charge. Well, that means if you have a molecule like acetone, the net result is that you have some negative out on that oxygen, some positive on that carbon. And it just stays there. It doesn't go anywhere. Well, charges can be attracted to opposite charges. So if you were to have another acetone, it's also going to have a partial negative and a partial positive. Opposite charges can be attracted to each other. This is an intermolecular force. This lets the two molecules be attracted to one another. They actually pull towards each other. So if you were to just have an acetone and another acetone, and they drift around randomly. If the negatives got near each other, they'd push away. But if they pass near each other and line up in such a way that they start being attracted to the opposite charge, then what will happen is that molecule will pull in a little bit. They'll spend time, they'll bounce off each other, but they contract, they get nearer to each other. The net result of this is that your molecules are drawn. As you have many molecules in a sample. So imagine this is a beaker full of molecules. What keeps that together? Why does water make little droplets on a surface instead of just flowing out into affinity? Is that they pull on each other. They pull in. All of these are on average pulled towards all the other ones. And so over time, they contract into little droplets. Intermolecular forces is what holds molecules together. Polar bonds are very strong at doing this, but they're not the only way. So we're going to investigate a little further into that. So what are the polar bonds that we expect in organic chemistry? Well, we're carbon-based, so almost everything is carbon to some other atom. So we've got nitrogens, we've got oxygens, we've got halides. Now you can also have things like oxygen to hydrogen, nitrogen to hydrogen, fluorine to hydrogen. We don't get lots of the other atoms combining. It is possible to get NO and things, but these are the majority of the ones we'll see. For our purposes, what we discover is that carbon nitrogen, carbon oxygen, and carbon fluorine are all imbalanced. In fact, let's draw that a little bit descriptively. Well, fluorine is more electronegative than oxygen, which is more electronegative nitrogen. So there's a little bit of negative on the nitrogen, there's more negative on oxygen, and there's more negative on the fluorine. Comparatively similar ideas with the positive on the carbon. CF is a more polar bond, and so it'll have a stronger effect on inducing these dipoles than the others, but any of these three are pretty darn effective at it. Additionally, OH definitely favors out towards that oxygen, so big partial negative, partial positive on the hydrogen. Same deal with the nitrogen, partial negative, partial positive, and the fluorine even bigger, and I've made this a little too close. But the idea is they can also cause a dipole between oxygen, nitrogen, fluorine, and hydrogen. All of these are polar. However, carbon-carbon and carbon-hydrogen, they're very close, or they're absolutely close with the carbon case. Despite carbon and hydrogen being a little bit different, they're actually close enough that we consider them nonpolar. Nonpolar molecules do have a means to be attracted to each other, but it is a lot weaker than the polar molecules. And so if we think of ethane, well, we can kind of average ethane electrons like this. There's some positives in the nuclei, there's a bunch of negatives spread out around them. If you have a couple molecules like this, same idea, some negatives on the outside edge, positives in the middle. These are balanced. There's no actual net charge. There's no permanent area of more negative and permanent area of more positive like we see in a polar bond. But what can happen is if you ever imagine carrying a bucket of water and you suddenly stop and it sloshes forward and backwards, it can imbalance for a minute. And electrons, when they're in their orbitals, are honestly described a lot like a fluid. They have a volume and a wave and they oscillate, and the result is bumping into each other, random thermal chance, anything like that. One of your electrons can get bumped out of the way. The net result is that it moves over here for a little bit. Well, this creates a side that has a little bit more negative suddenly, and a side that has a little bit more positive. This is a fraction of a second, nanoseconds and less, but for a brief moment, it has a dipole. It's called a temporary dipole. It's small, it's very short-lived, so it's nowhere near as strong as the permanent dipoles we saw for oxygen and carbon, but it does exist, and as long as it exists, this means the electrons on the next atom can be a little attracted to it, which makes their own electrons shift a little, which causes a little bit of imbalance on this molecule, which causes the next one to do the same thing. And so you end up creating a bunch of dipoles spread between multiple atoms in series like this. Now, a nanosecond later, it's gone. But for that brief moment, the molecules drew towards each other. So this is how you can actually get nonpolar molecules to stick together. So this is polarity and the idea of polar and nonpolar bonds. We're going to dive deeper into it in our next section.